is Tam, and I'm going to be talking about the flatten function. The flatten function turns an image into a black and white image filled with 0, 1 matrix. The first line of code reads the image and turns it into a matrix. The second line of code checks each pixel in the image and see if it's greater than an arbitrary number. In this case, the arbitrary number is 169. So if any pixel that's greater than 169 becomes a 1, and anything less than that will become 0. So at the end, we get a matrix that is filled with 1, 0, which is a logical matrix, which is also a black and white image.
I'm Salim, and I'll be discussing the expand function. The purpose of the expand function is to ultimately convert the black and white images into color. We started this off by first creating a logical matrix and converting it into a class double logical matrix. We then created a 400 by 400 matrix with 3 layers all filled with zeros, as can be seen by the third line in the code. Then from the matrix, we converted all of the 1s into 255. The 1 represents white in the black and white images, and 255 represents white in the colored image. Then we created 3 layers, red, green, and blue. Then we inputted the logical matrix into each of the layers, and this gave us the colored image that we were going for.
Hi, I'm Omar Nam, and this is the odd-even embedding technique. The odd-even embedding technique looks at a specific layer of the normal image matrix. When you look at black pixels that are equal to 0, if it is divisible by 2 and has no remainder, it's even and you minus 1. If the remainder is 1 after you divide it by 2, it's odd and you subtract 0 from that pixel. For pixels that are white which are equal to 1, if it has no remainder, it is an even number and you don't subtract 1. But if the remainder is 1 after you divide it by 2, it is odd and you subtract 1 from that pixel.
For our second embedding technique, we check each pixel in each layer by dividing it by 4. If the pixel originally is 0, which means black, we check the remainder of it after we divide by 4. If it's either 2 or 0, it means that it is an even number, and so we have to subtract by 1. If the remainder is not 2 or 0, then we don't need to subtract by 1. But for white pixels, which is 1, after we divide by 4, and if the remainder is either 2 or 0, we don't need to subtract by 1. But if it is not remainder 2 or 0, then we have to subtract it by 1 to make it an even number. So for our third technique, we check each pixel in each layer by dividing it by 8. For black pixels, if the remainder is either 0, 2, 4, or 6, after dividing by 8 is an even number, so we have to subtract it by 1. If the remainder is not 0, 2, 4, or 6, is an odd number, thus we don't subtract it by 1. For the white pixels, which is equal to 1, if the remainder is either 0, 2, 4, or 6, we don't subtract by 1. While if it is not 0, 2, 4, or 6, we subtract it by 1 to make it an even number. And for our fourth technique, we did a similar thing, but instead of dividing it by 8 and checking the remainder, we divided by 10 and checked the remainder. For the recovery techniques, it is the same for all the embedded techniques. Basically, we created a 400 times 400 matrix filled with zeros called the recovered image. We check each layer's pixel and see if it's an odd or even number. If that pixel is an odd number, then the recovered image pixel is 0. While if the pixel is an even number, the recovered image pixel is 1. And then we ran this recovered image in the expand function.
This is the GUI, and we're going to show you how it works and functions. First, when loading the image, we use the UIGetFile function to browse through the saved images and display the normal image into axis 1. We use the same function for the hidden image, but display it on handle axis 2. Next, we choose an embedding button, the odd-even red layer, to change the pixels of the normal image with the hidden image, thus creating an embedded image. We could choose as many embedding buttons to change the pixels of the normal image. After the embedded image loads from going through the loop that creates this image, we save the embedded image using the onWrite function into our picture files. We load the embedded image using the same technique to load the normal image. we choose the recovery buttons that correspond with the embedded buttons to extract the hidden image in the embedded image. And this is how our GUI works, and we can show you another example. This GUI example, we're going to show you how the GUI works with two embedded buttons. So we begin the same way as last time. We load a normal image. We'll also load a secret image. This time we click the divisible by 4 blue layer button and the divisible by 8 red layer button. And the embedded image is as shows. We save the embedded image, and now we can load it. We click on the divisible by 4 blue recovery button, which corresponds to our embedded recovery button, and the divisible by 8 red recovery, which also corresponds to our embedded function button. And this is the hidden image